All right, welcome back everyone to What Are Quantum Computer Series. In the previous video, we went over what algorithms are, the purpose of how an algorithm can be used in real life, and we even did a little coding activity to represent an algorithm. Now in today's video, we'll be going over what a qubit is. Before we dive deep into the content, let's do a quick video review. So first off, we'll be starting with what is a classical binary bit, what is a qubit, the phenomena of superposition, Paul Dirac and the Brockette notation, Qubit and Dirac's notation, and the difference between a qubit and a classical bit. So what is a classical bit? Well, a classical bit is a binary piece of information which can either be 0 or 1. A classical computer only has memory made up for bits which either hold 1 or 0. And the classical memory is used to manipulate the states of 1 and 0s to crunch through operations. Remember, 0 and 1 are both its own states. What is a qubit? Well, a qubit is a quantum bit that is a basic unit of information in a quantum computer. The quantum bit is a counterpart in quantum computing to the binary digit or bit of classical computing that we discussed in the algorithm video. As mentioned in the previous video, a bit is a basic unit of information that is in a classical computer. Well, the qubit is also a basic unit of information, but it's for a quantum computer. A qubit has a spinning electron or particle that adopts two possible states of 0 and 1 all at the same time. This action of the qubit staying in both states simultaneously is called superposition. This phenomenon of superposition would be different than the classical binary bit, which can only be in either of the two possible states of 0 and 1. So, the phenomenon of superposition. Qubits are stored in superposition states in which there can either be in a state of 1 and 0 at the same time. As a result, this enables a qubit to perform multiple calculations simultaneously on a quantum level. This is how qubit superposition could find the one outlier in all the endless solutions. What could we use as an example? Well, let's say if we're trying to find the one chemical reaction compound that can cure cancer, and we input the numerous solutions that consist of different chemical reactions. The qubits can use its laws of superposition to check all of the solutions at the same time and find the main cure in minutes, compared to the normal bit, which has to manually check each and every solution. That normal bit would take thousands and thousands of years. Now, qubits can also speed up finding the main resolution out of a number of solutions, like an infinite number of solutions. Okay, Paul Dirac and the Brockette notation. So, as we'd mentioned about what the superposition of a qubit is, it is also represented by Paul Dirac's Brockette notation, or the Brockette notation. The Brockette notation was established by physicist Paul Dirac in 1939, also known as the Dirac notation. Brockettes are symbols in quantum mechanics which specify the multiple states of a system. A ket is the form of 0 or 1, where 1 and 0 are the states of the quantum system, and that's the same thing for a bra. Right, so why don't we go back to when we were talking about a qubit being an electron with spin in superposition. Now, that spin is a leveled / linear combination of the two possible states. That linear combination is the variables that represent these states with addition. Spin up, or 0, is the linear combination variable of x, and spin down, 1, is the linear combination variable of y. Now you could name it anything since they are variables. Now, if a qubit is in superposition of the Brockette states simultaneously, this means that the qubit would just add up these two states, being 0 plus 1, or x of 0 plus y of 1. Again, remember, superposition is where both states of 0 and 1 are looked at simultaneously, spin up and a spin down, which is why both states are being added. So, what is the difference between a qubit and a classical bit? Well, qubits are in a superposition of both states, whereas classical bits are not. As we mentioned, a classical bit is only in either a state of 0 or in a state of 1. Now, every operation on the qubit is done at both states at once, right? Which is why qubits can pack more storage capability and information than a classical bit. Whereas bits are really slow, and multiple bits are required to complete the most effortless equations on a classical computer. Whereas qubits are much more faster than bits on an astronomical scale and can solve substantial equations in an instant. Here we have a chart that shows the difference between a classical bit and a qubit. On the left, why don't we take a look at the classical bit? Well, the classical bit is a subset of a qubit, and the actual fraction of a classical bit is either 0 or 1. So how this happened? Well, it's because as a classical bit, as we mentioned, is a subset of a qubit. It is because while a qubit is in both states of 0 and at the same time, a classical bit can only be in either states of 0 and 1 at an instance of time. So does that mean? Well, back to our linear combination variable of being in either state of x or y, when we are in a state of x, it could only be 0, whereas for y, it would only be 1. And then same thing for x, where x could only be in a state of 1, y could be in a state of 0. Now, this is different for a qubit. Might I explain why? Well, the x represents the fraction of the qubit that is in the state of 0, and the y represents the fraction that is of the qubit in the state of 1, or vice versa. And the superposition of an x and y is a non-zero number. As we had mentioned, x of 1 plus y of 0, which is how a qubit is really just a complex number. So as we see in this chart, x and y can both be 0 and 1. X and y could also be 1 and 0. Thank you for watching the video, and here are our citations. Till then, I will be seeing you in the next video.